Hello, thank you for joining me. My name is Allan Fulton. I am an Irrigation and Water Resources Farm Advisor with the University of California Cooperative Extension. I am located in Red Bluff, California in the northern Sacramento Valley and serve a 4-area rural ag counties, Tehama, Glenn, Colusa, and Shasta. The focus of my talk today will be centered around irrigation of tree fruit and nut crops in drought times. And I will touch on 4 talking points through the presentation. I'll start with trying to give a recap of the drought status within the narrow context of orchard crops. I'll speak to some conservation measures that have broad application across any type of tree fruit or nut crop. And then I will speak directly about some specific crop management experiences in almond, walnut, and prune, which are among some of the major crops grown in our area. From this presentation, I also hope that you will find additional sources of information and technical support contacts to follow up on later. The drought status in the Sacramento Valley within the context of orchard crops is such that I would describe the situation as not as extreme as other areas, with the emphasis on the word yet. Most growers of tree fruit and nut crops will attempt to assemble enough water to irrigate and to achieve competitive yields and good quality fruit and nuts in 2014. They will also be mindful in their irrigation management to manage water in such a way to promote enough shoot growth and floral bud development to have a chance for high fruit and nut yields in 2015. With permanent tree crops, we have to be cognizant that we are not only managing to complete this year's crop, but we are also managing to set up the potential for next year as well. So the main approaches to drought management in 2014 in the Sacramento Valley is greater reliance on groundwater to offset the shortage of surface water supplies, and to implement a variety of water conservation measures and strategies. The goal of the conservation measures and strategies is to preserve as much groundwater in the aquifers as possible so it is available to cope with the uncertainty of 2015 and beyond. We know that we are definitely in a drought now. We are concerned about it, and we do not know what holds for us in the years to come, whether the drought will continue. So now I would like to discuss some conservation measures that have broad application across many types of orchard crops, fruit and nut. Let's start with where are we as far as adoption of efficient irrigation methods. This graphic comes from the California Department of Water Resources Northern Region. It represents land use and irrigation method surveys of the 5 northern counties of Colusa, Glenn, Butte, Tehama, and Shasta. And it represents a little over 243,000 irrigated acres of tree crop production in the area. If you study this graphic for a minute, particularly the legend on the right, the main point of this graphic is that about 80% of the tree crop production in the northern Sacramento Valley is irrigated with either micro sprinkler irrigation, buried drip, or permanent mini sprinkler type irrigation. All of these methods share in common that they provide very precise application rates, very low precipitation rates, typically less than 1/10 of an inch per hour, and it gives the farmer the greatest control and management ability of any other irrigation system. So in the last decade or two, the tree fruit and nut crop growers have come a long ways in adopting efficient irrigation methods. There's about, as you study the pie chart, the orange and sky blue color between 10 o'clock and 12 o'clock represent the portion of acreage that is hand moved, sprinkler irrigated, border strip irrigated, and furrow irrigated. And certainly in light of this drought, there will probably be incentive for further conversion of these irrigation systems to the more efficient and better controlled systems. So beyond the irrigation method that we're using, the next management practice that we can consider is give attention to the uniformity of which we apply water. This cartoon illustrates the concept of non-uniform versus uniform irrigation. The goal of a efficient irrigation system is to apply the water uniformly from one tree to the next throughout the orchard. In this cartoon, we have a situation where more water is being applied to this tree, and it's demonstrating that there's a potential of deep percolation losses below what would be the primary root zone of the tree. And then in the next case over, we see actually under irrigation. So with systems that are not applying water uniformly, we can get a worst case scenario of losing water in some places and having inadequate water in others. A system that applies water uniformly has a better chance to apply water efficiently and grow better crops. So irrigation uniformity can be measured in the field. We have an index, it's called the distribution uniformity, and it's defined here for you given the arithmetic formula. It is defined as the average applied water in the lowest quarter of the field divided by the average of the whole field. So typically the way these systems work is the systems tend to apply more water near the pumping plant and the filter system, and as the water is distributed out and away from the pumping plant, it distributes less water. So when we have a distribution, in this example, we have two different irrigation systems with different distribution uniformities. We want to apply on average a 1-inch irrigation to replenish the water. With a 90% uniformity, what it shows us is the maximum amount applied at any point, any portion in the orchard is 1.12 inches and the least is 0.9 inches, about a 10% variation from either side of the target. But when we have a lower distribution uniformity of 70%, we see that we can get much more variation, as much as 1.4 inches in the upper quarter of the orchard and as little as 0.7. 30% to 40% off the target application rate, and more importantly, twice as much water applied in one area than in another area. And as a result, we have risk of both harming the orchard from over-irrigation and holding back production potential by under-irrigation. These are data provided by the Tehama County Resource Conservation District, the Irrigation Mobile Lab. It's a public entity that's been in operation for about a decade now. I will provide more information on how to contact them later, but they provide a free service to growers by going out into orchards and actually evaluating how the system is performing. And the key pieces of information that you get is an understanding of the average hourly application rate of your irrigation system and a measure of that distribution uniformity. This graphic shows, if we concentrate from this point to the left, this graphic shows what their observations in orchards over the last decade their measurements and evaluations in the last decade have shown. For hand move, sprinkler, and flood, you can see, as the pie chart suggested earlier, much fewer numbers indicated by the purple bars, much fewer systems evaluated, and you see by the red bars the irrigation uniformity or the distribution uniformity is much lower, ranging from 39 to 55%. Now, as growers have adopted new methods of irrigation, drip and micro sprinkler, these systems over here represent these newer type, more efficient irrigation systems. You'll see the number of evaluations by the purple bars are much higher, and you'll notice that the irrigation uniformity, the distribution uniformity, is also much higher, ranging from a low of 82% to a high of 92%. Irrigation uniformity has to do with, first, the design of the system, and then the second, the care and maintenance of the system. Once the system is in place, it needs to constantly be checked for plugs, leaks, breaks. This photo shows some of the kinds of problems that can be found with systems. We see biological plugging in the upper left. We see particle plugging from particles that get past the filters, chemical plugging, and we just see general wear and tear and breakage in the lower pictures. So maintenance is the key to high performing, achieving uniform irrigation application and being efficient. As I said, technical assistance is available to evaluate irrigation systems. The service is available through the Tehama County Mobile Irrigation Lab, founded since 2002. It has been serving the Tehama, Glenn, Butte, and Shasta areas and is hoping to expand this year. And the current contact is Kevin Greer, and his information is given to you in this slide. So moving from the emphasis on irrigation uniformity, the next management practice that we can apply is making informed irrigation scheduling decisions. That is, informed decisions on when we irrigate and how long we run the system and how much water we apply. Today I'm not going to teach on the different tools and how they work. My goal more is to make you aware of what's available and how to find more information. Basically, there are three approaches that any one can be used, or they can be used in combination. But there is information available that provides real-time estimates of crop water use, also known as evapotranspiration. We have tools such as the pressure chamber that can be used as crop stress detectors. There's another presentation in this series that goes in great depth on this subject. And we have soil moisture sensors on the left. That is an example of a dielectric soil moisture sensor. Real-time crop ET estimates for fruit and nut crops are provided throughout the Sacramento Valley. They are provided in various formats. They are provided every 7 days through the irrigation season. On the left-hand side of this slide, you'll see a sample report that can be received at your PC or on your mobile device by email. It provides the past 7 days of water use, the cumulative water use since the crop is leafed out, and gives a 7-day forecast of water use for the major tree fruit and nut crops grown in the Sacramento Valley. As I said, it's available in email format. It's also posted to a website. The web address is given there, and it is also published in 8 Northern Sacramento Valley newspapers each week. This information is a cooperative effort with the Department of Water Resources Northern Region and UC Cooperative Extension. This slide provides an information update on a new publication by the University of California Agriculture and Natural Resources, publication number 8503. It is currently in press. It's expected to be released as a free online publication in May 2014, and the link to access that free publication is given on this slide. The title of the presentation is Using the Pressure Chamber for Irrigation Management, Walnut, Almond, and Prune. I am a co-author along with my colleagues Joe Grant, Richard Buckner, and Joel Connell. This publication supports the information provided by Dr. Shackle in the series on assessing crop stress. It also gives interpretive guidelines for what the readings mean for these 3 crops in particular, and it provides a research discussion, the basis of the research, and how the interpretive guidelines came about. So now I'd like to move into some on-farm experimentation with efforts of trying different strategies to conserve water in times of drought. The materials that I will cover in these next slides are discussed thoroughly in the previous publication that I shared with you. We'll start with almonds. This table provides the average annual almond water use for mature bearing almonds. And if you look at the very bottom under total, you'll see that on average, almonds in the Sacramento Valley use approximately 48.5 acre inches of water per year. And you can look at the pattern a little bit more. You can see that it shows that water use in early March is much lower at 1 inch. You can see it reaches a maximum in mid-July of close to 4.8 inches, and then it declines again by fall time and reaches a low in November of 0.29 inches. So one of the concepts that we experimented with from 2004 through 2008 was the concept of regulated deficit irrigation in almond. And what the goal here is to withhold water to the extent that it creates mild or moderate stress and reduces the actual water consumption or evapotranspiration, symbolized by ETC, and that it reduces it to some controlled degree. We withhold the water at the least sensitive crop growth stage and regulate the level of crop stress allowed. The goal is to minimize the impact of reducing irrigation on productivity. So these slides are results that have been published in the University of California's quarterly publication called California Agriculture. It was published in volume 65 in April through June of 2011. And what it shows here, in this experiment, we had 2 irrigation treatments. One we called a control, and one we called a regulated deficit irrigated treatment. These were large plots and replicated 6 times in this experiment. The data over here is pressure chamber data showing the seasonal trends in midday stem water potential. This was what we used to determine the stress levels the trees were under and to regulate the stress and make irrigation decisions. The first green line is a predicted line using a model. That is what we think the lowest stress level could be in the orchard under the particular growing conditions that year. The yellow line is the measured stress in the orchard of the control treatments. And then the red line are the measured stress levels in the regulated deficit irrigation, where we purposely withheld water. And what we did is we targeted hull split reduction in water occurring sometime after the 4th of July, depending on the variety, and extending for about a 3 to 4 week window. We purposely reduced the amount of water that we applied and created the crop stress. And you can see the separation between the control line and the RDI line. Once we approached harvest, when hull split was over, we resumed normal irrigation and tried to recover the stress. You'll also notice that in both treatments, the control and RDI, there was crop stress that was unavoidable during the harvest season. The results of the experiment, we carried this strategy for 4 consecutive years. And what you see here is a reduction in the consumptive use of the water by the almond trees on the order of 10 to 15% by purposely inducing a modest level of stress. When we looked at the field harvest yields of these large plots, what you see here, these were young trees coming into full production, and what you see is a steady increase in yield from 2004 to 2008, and there's no separation between the control treatments and those that we purposely stressed with the RDI strategy. So a key conclusion in almonds is that during a drought, it may be possible to irrigate at levels of about 10 to 15% less than full ETC when timed at the proper crop stage, which in our experience was at hull split, and have minimum impact on the current year crop or next year's crop potential. With larger cutbacks in water, impacts on production will likely be more significant than what is reported in this study. Moving on to walnuts. This table gives a similar piece of information as for the almonds, gives a breakdown of the annual average ET for walnuts grown in the Sacramento Valley. And you'll see it down at the bottom, the total is about just under 41 inches, which is significantly less than for almonds. And the reason for this is that we grow later leafing walnut varieties that don't break dormancy until around April 1st and do not establish a tree canopy, till probably mid-April to early May. Whereas in almond, they bloom in latter February and they develop a canopy by mid-March. And so there's about a 45-day head start on their water use. And so water use in almond is higher than walnut. So we tried a similar regulated deficit irrigation approach in walnut. We imposed 3 levels of crop stress for 3 consecutive years in 2 different walnut orchards, very different conditions, and I will describe them a bit more. The strategy was to increase crop stress as the season progressed. In essence, we did not want to stress the trees in the months of April, May, and part of June. As this is when shoot growth occurs, we were trying to promote shoot growth so that there would be good floral bud development for next year's crop to set up the potential for a good crop next year, as well as manage the current crop year. To impose these treatments, we monitored the stress levels of the trees with the pressure chamber and stem water potential, and we measured the applied water with flow meters. There were 3 treatments: a low crop stress level, where with the pressure chamber the seasonal average stayed around 4 to 5.5 bars, and we applied about 36 to 42 inches of water. The second treatment was a mild crop stress, where we allowed more stress over the season, a higher average of 6.2 to 7 bars crop stress, and we applied less water, on the order of 22 to 28 inches of water, depending on the year. The final treatment was a moderate stress, where we withheld water even more, allowed greater stresses, measured up to about 7.5 to 8.6 bars, and we limited the applied water to 18 to 23 inches. So here are some results from the experiment. It was conducted over a 3-year period, 2002 through 2004, where we imposed those treatments and repeated them. One location was in Tehama County. It was in a young developing chandlered orchard from 8th to 13th leaf. It was just coming into production, full production. And it was on west side soils, terrace soils that were shallow, had gravel and lower water holding capacity. The second orchard was located in San Joaquin County. It was an older, mature orchard, over 20 years old, and it was located on deep alluvial loam soils with high water holding capacity. As you look through this data, you'll see the average stress levels for the different treatments. And then if you look at 2002, the field yield measurements, you'll see that neither orchard showed a reduction in yield in the first year of imposing the stress and withholding water. And that was to be expected. It comes back to that before you see yield reduction, you have to have a year of stress and cut into the shoot growth and the bud development and reduce the crop load that's in the crop. The crop load in 2002 was established by the management in 2001, which was before the trial. So we continue to look at the data. We see in 2003, we start to see the effects of the withholding water, particularly in the Tehama County orchard with the shallow soils and lower water holding capacity. Following 2 years of withholding water, we see a separation in the yields on the order of over 1,000 pounds to 1,600 pounds per acre, which is highly significant from an economic perspective. Now, as you look down at the San Joaquin Valley, San Joaquin County orchard, you'll see that the yields are starting to show a numerical decline, but they were not repeatable, and the variance was such that it suggests they were not significantly different. So at this site, with the deeper soils, we went a second year without seeing a significant effect on walnut yield when we withheld water. Now we look at 2004, the third year in the Tehama County orchard on the shallow soils. The effect was exaggerated. Even further, you can see that the difference between the low stress and the high stress is on the order of 9/10 of a ton, 1,800 pounds, which again is economically very significant. Then in 2004, we see that the San Joaquin County orchard is actually now starting to show a significant response to withholding water as well. Overall, after 3 years of imposing these stress treatments, we measured between an 18 and 42% reduction in yield by the third year of stress. So a key conclusion in walnut is that walnut is more sensitive to water deprivation than a crop like almond. And so far, the research that has been done has not identified a strategy to consistently hold water at levels less than full ETC, evapotranspiration, and not adversely affect yield or nut quality. A couple other refined points to take from this experiment is impacts on production can be acute, in other words, quick, occur more quickly, or they can be chronic and be more delayed. And this appears to be related to water holding capacity of the soils and the associated root development. Because we saw that effect of the differences between sites and the soils and the age of the tree and presumably the root development, it may be possible that one tip to help you through a drought is to reallocate water from more deeply rooted orchards on deeper soils to other orchards on shallow soils to lessen the impact of drought on ranch-wide production. In order to do this, though, with success, direct measurement of crop stress would be very important to help identify these opportunities. So, the final crop that I wanted to touch on is French prune. French prune has a water use patterns similar to walnut. If you look at the total, the seasonal water use is a little over 41 inches. Although it is a smaller tree and the orchards look much different than a walnut, what is happening is they are longer season. They leaf out and establish canopy and use water beginning in early March, where walnut doesn't really get going until mid-April. And so we get some compensation there. Now, in French prune, we conducted a case study where we implemented guidelines from previous research that suggested a way to deficit irrigate prune and actually save water and gain benefit. So the graphic on the left are weekly stem water potential measurements indicating the level of stress that this prune orchard underwent during the course of the season. If you look at these stress levels, through May, it was pretty much in low, mild stress levels. Then in June, there was a slow, subtle decline in stress from mild to moderate levels, and then there was significant stress right around harvest time. You can read further on these guidelines and compare the levels in the graphic. At the bottom is a simple water budget that shows how the irrigations were actually handled. Almost 27 inches of water per acre were applied to this orchard, which is considerably less than the 41 inches of annual average ET. This orchard, by monitoring soil moisture, we measured this orchard received an additional 5 inches from soil storage from the winter rainfall, and it also received an additional almost 8 inches of water from rainfall that occurred in the spring after the orchard had leafed out. 2011 was a late wet spring. When you add those numbers up, they total about 39 inches, which still comes in below estimates of ET. Here's the 4-year trend in French prune yield for this orchard. The case study orchard is represented by the blue bars. This orchard averaged around 3.6 to 4.4 dried ton per acre each year that we imposed that drought strategy, that regulated irrigation strategy. By comparison, you can see that this orchard performed above the average yield for prunes in Tehama County on those respective years. So this suggests that allowing some stress to conserve water did not impact the yields. A key conclusion from this case study is that during drought, it is possible to irrigate at less than full ET, allowing mild to moderate crop water stress gradually from mid up to harvest time and have little or no impact on the current year crop or the next year's crop potential. Fruit yields remained constant over 4 years. Fruit size was between 54 and 60 count per pound, which is large and desirable by the processors. So the deficit irrigation had no impact on fruit quality. We actually improved sugar content of the fruit and reduced the drying costs at the dehydrator for the grower. In order to impose a stress treatment like this, save water and manage drought situation. Again, direct assessment of crop stress was important. So to wrap up my presentation, I would just leave you with the thoughts that increased reliance on groundwater is currently lessening the impact of drought on fruit and nut crops in the Sacramento Valley. There are conservation measures and management strategies that are and should be used to save as much groundwater as possible for the uncertainties of 2015 and beyond. Focus your attention on irrigation uniformity, maintain your systems, check them, and know that they are working well. Incorporate information and technology into your irrigation scheduling decisions. Utilize the ET information. Consider using crop stress detection methods and soil moisture monitoring and incorporating them into your water management. Keep in mind some crops can tolerate water stress better than others. Employ management strategies to capitalize on this to better manage the drought. Thank you for joining me in this presentation.